Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you're doing good. In this, we're going to maximize the number of target nodes after connecting trees to. You should have watched connecting trees 1 for sure. I will not repeat stuff here. Now, the only change from this problem to the new problem is that node U is the target to node V if the number of edges on the path from U to V is even. Earlier it was K, or I should say the node V should have a distance of less than equal to K, then we're considering as a target to the node U. But now if the distance is even, then I will consider that as a target. So if we bring back, now we were easily be able, like we easily were able to identify a golden node here, which will give me the corresponding maximum, maximum number of nodes which are a distance of less than equal to k minus 1. Can I use the same thing here? There are multiple other stuff other than this. What I mean by multiple other stuff? For example, let's bifurcate this question also into two problems as we did previously. For this specific node U, I will compute the answer for this specific tree and then I will choose something from tree 2. Still, there's a question, choose what? But let's firstly bring back that what will be the answer for node U. Now, the problem has changed to going towards the distance should be even. It should be even. If I give you a quick cracks, then you will see that for node 0 answer is 8. As you can see, this is at an odd distance, wrong. Even distance, okay. Odd distance, wrong. Even distance, okay. Even distance, okay. So for this, the count, again, these are same variables which we took previously also in the problem number 1. Count for this specific node, which is 0, I should say, is actually 3. Considering, again, I'm not saying this should be there, but considering if I attach this node with the node 0, then I need to get again the even distance for, can you just see, even distance from this node will actually be nothing but odd distance from here. So okay, odd distance, one this one, one this one, this is not even, okay, this is also even, one this one, even, oh, odd, and then odd. So 1 2 3, 3 from here, 1 2 3 4 5 6 7 8. Answer is 8. Now, very easily you were able to identify one very basic stuff, that from every node, from this specific node U, you have to find out how many number of nodes are there which are at an even distance. I can simply do anything, either a BFS or a DFS, from this node U to find that at a distance of even, and on an even distance, as you can see, the distance is 0 here, the distance will be 1 here, the distance will be 2 here. At an even distance, number of nodes, that will corresponding count. But as I was doing in the earlier approach, where I was going on and doing a graph traversal from every node, that incurred a complexity of O of n square, and that also worked in the previous problem. But here, because of the constraints, that will not work. Obviously, I have to think of something better. Before I go on to thinking of something better, and ultimately my maqsad here is for this specific node, ultimately get me the count. The count is from this node, what or how many number of nodes are there which are at an even distance from this node U. But even if, let's say, I'm able to achieve this, although I have to achieve this, and that's a question in by itself, even if I'm able to achieve this, I still have to figure out, is there anything as of a golden node here? Can you think of the possibility right here? Can you think of the exact same thing which is unique to this problem but also similar to the previous problem? Simply, if you remember, I was checking off what is the golden node in this tree 2, which is obviously golden node I defined as a node which has k at a distance of k minus 1 maximum number of nodes. Ultimately, maqsad is still same. We have to maximize the number, which is the answer of I. So from this, I will have to again find a golden node, but here the golden node definition will change. Golden node will be a node that who has the maximum number of nodes at a odd distance from that node. And again, here I am computing the even distance, here I am computing the odd distance. I have to still try to optimize my answer that I am computing that distance for all the nodes in O of n time, but the problem is still the same. I'll have to compute the odd distance from every node. I should say, okay, for this node, the number of nodes at an odd distance. I have to compute this for every node from tree 2. For tree 1, I have to compute from every node number of nodes at an even distance in tree 1. When I have both of them, I will find a golden node in tree 2, which has the maximum number of nodes as neighbors in odd distance from tree 2. I'll simply attach with that specific node, and that will be a golden node. Same concept or same crux as what we saw in the previous example. Now we know that how we will be able to achieve it, but we are able to achieve it in a time of O of n square plus m square. This will obviously not work. How we will optimize our answer is the question. Now, to optimize the answer, the thing which I have to bring out now, again, as we have to compute the same thing for both tree 1 and tree 2, the only difference is I have to compute here the odd distance node, here I have to compare the even distance node. Now, if I have to compute the same thing, now let's focus only on tree 1 and let's try to find that how I will compute that at odd distance, even distance stuff for every node in tree 1 by maybe using some pre-computation stuff. If you are not familiar, this is the kind of stuff where you have to do some pre-computation, memoization. That's simply nothing but DP on trees. Although, don't get scared with this term. It's simply, we will see how we will simply can use or leverage other nodes to efficiently compute the number of even distance node or odd distance node. Let's see with the help of an example. So if I take the example itself, I will have again for before we go on to, let's see the maksat. Maksat here is I have a node 0, node 1, node 2, node 3, node 4. I should be able to figure out total odd nodes, total number of nodes at odd distance from node 0, total number of nodes at an even distance from node 0. Aryan, but you only need even distance node, right? Obviously, I need it. But if you remember, tree 2 would need odd distance. So I am taking consideration that, okay, I am computing both of them. And you will see this will be required no matter if T2 would have been there or not. Still, this would have been required. We will see. But firstly, I am getting my maksat done. Same way, I will get, okay, this is for T0. This is, let's say, I should say, what is T? Okay, this is nothing but odd, total even. Same way I compute total odd, total even, total odd, total even, and same way total odd, total even. Same way total odd and total even. Now, you know that if I do a total odd, total even from every node, that will compute O of n square time, no matter if I do a BFS or a DFS traversal. Obviously, have to make the benefit of something. And I say something, I mean, I will simply do a BF, I'll simply do a normal traversal, obviously a DFS traversal, simply a simple traversal on the tree, and then try to leverage how I can leverage my nodes. But if you say a simple normal traversal, in a simple normal traversal, what you do? You simply are on node 0. You will go on to your child, then come back, then go on to child 2, then child 3, then child 4, then come back. Which means that you leverage the information from your child. How I can leverage the information from my child? If I ask that rather than total, let's have partial odd number of nodes at the odd distance. What will be there? Obviously 0. Number of nodes at the even distance. Obviously one node itself, because it's a leaf node. For the leaf node, there are no childrens. Again, I'm simply doing a simple traversal. If you know a simple traversal looks like, I go on to there, then I go on to 2, then 3, then 4, and then come back. This is a simple traversal which I'm doing, which means I can only leverage my children right now. That's it. So for node 1, he has no children, but number of nodes at the even distance from me is only me. So answer is 1. Now I'll go back to my parent, but as it's a simple DFS traversal, so he will go here, and then go here too. Then again come at 3. Okay. Then obviously partial answer will be nothing but 0, but even will be nothing but 1. 3 itself. Here also 0. Here also will be 1. Again telling number of nodes at the even distance. For 2, Again, when I say partial answer, which means only a subtree I'm considering, and that's only what I can consider when I do a simple traversal. And I'm simply also taking leverage of my children, what value they're bringing me. For node 2, now for me, I have to get the answer considering only the children of node 2. How I will leverage it? For node 2, if I want to compute the partial answer, just see one thing. Number of nodes at the odd distance are 0, right? Number of nodes at the even distance are 1. So if I ask number of nodes at the even distance are 1, which means 3 itself. Number of nodes at the odd distance are 4, which is, okay, sorry, even distance are 4. 1, which is the node 4 itself. So for node 2, I will ask my children, which are again my children, only my children. My children are at distance 1. My children are at the odd distance from me, which is 1. 1 plus odd number. 1 plus odd number gives me even number. 1 plus even number gives me odd number. So for me, the number of things in the odd distance from me are even of my children. So I'll take the summation of even children. Okay, 1 plus 1. This is P1 of, I should say, P3E and P3E. For the odd distance from me, again, obviously, myself, I am at the even distance from me. So I cannot count myself here, but I will count the even. I'll count the even of my children. I'll count the even of my children to get to know the number of odd ones for me. Same way I will do it for even, but the only caveat here is for even, you will have to count yourself also because you are at a distance of 0 from yourself. But because you want even, you will have to count the odd of your children. Again, this will be make sense when I will go to 0. So what I will do, again, this will be nothing but 2 here, and for PE, which means, as you can see, 0 plus 0, it will be 0 plus 0, which is nothing but 1, which ultimately indicates what? Even, only 2, odd, 2 3 2 4. Now for computing the answer for 0, again same stuff. To compute the odd one, I will go on to children even. Again, only my children, which are at a distance of 1. At a distance of 1, I'm going to go on to only my children. I will say, okay, 1 to compute the odd, I'll go on to even, and the even is 1. So even 1 plus 1 2. Again, for me, odd distance to myself itself will be 0. This is with myself, and there's no contribution with myself for odd. But for children, it will be 1 plus 1. Oh, answer is 2. And as you can also see, 0 at a distance, or I should say at odd distance, I have 1 and 2, which are 2 nodes. Same way, if I compute even, obviously I count myself first, which is 1. I count myself. Then I ask my children for odd. He will give 0. Okay. He will give me 2. He will give me 2. Answer is 3. What he gave as 2, which is the odd value, is odd distance from himself, which is, if I add a plus 1, it will become an even distance from his parent. That's the crux. So what this 3 indicates? 3 indicates from node 0 is the first node, then node 3 is the next node 4 is the next node. That 3 nodes are there. So with this fact, again, if I show you the code also parallelly side by side, with this fact, what you did, you did a DFS 1. Again, you will do the same thing for tree 2 also. So you will see here, I have written tree 1, but it is a DFS 1. DFS 1 is simply computing the subtree kind of a stuff here. That's it, period. What he will do, firstly, he will update the even subtree 1 for that specific node by 1. If you remember, I will have to add a plus 1, for even, and have to add a 0 for the odd. Same I did here itself. I added a 0 for odd and 1 for even. Then I go on to all of my children. Obviously, the child should not be the parent. And then I will simply go on to my children, compute their values when their values are computed, which means while coming back, I will update the even for my subtree. How I will do it? Even for my subtree will be nothing but odd of my children. Odd of my subtree will be nothing but even of my children. Just adding it. Aryan, where is plus 1? Okay, plus 1 and 0 is already added when I did initialization. And that's how I'm computing it for my subtree. But this was not the problem. But the problem itself was for every node. Again, for node 0, I was able to achieve, okay, as you can see for node 0, the even node count or the number of nodes at the even distance, as you can see, were 3. If I just put it back and if I get this entire thing copied down below, so you will see, okay, copy this entire stuff and then let's paste it. Let's paste it here. So here we simply realize that even count here was 3, odd count, okay, sorry, odd count here was 2. Same way, even count here was 1, odd count was 0. Here also, even count here was 1, odd count was 2. Even count was 1, odd count was 2. Even count was 1, odd count was 2. But this even and odd count are for their corresponding subtree only. But if you remember, I want the even and odd count. I should say even and odd count represents at the even distance and at the odd distance what all or how many number of nodes are there. This is what I want. I don't want for the just the subtree for it. I want for the entire tree, which means for node 1 it should be like this, which means it should have the count for the entire tree. For node 0 it has covered it, but for node 2 it has not. So it has to also take in consideration the upper portion, which where is the actual crux or actual part lies. How I will do it. And to know that how you will do it, let's see that how I can leverage this information which I have computed before. What I will do, okay, I'm at the node 0. Okay, he knows that even is 2, odd is 2. For node 0, considering I started off from node 0, his total even will be 3, total odd will also be 2. Now I will go on to, let's say, here. Right, again, let me write it quickly down below also, that e equals to 1, o equals to 0, and e equals to 1, o equals to 0. It was a 0 0. Cool. Now, as I go on to the child, I have to compute its total even and total odd. That's my task. If this is my task, can I leverage this information? Can I leverage my parent? Can I do it? Yes, you can. How? Let's see. So if I go on to my child, again, this is the node, this is my child, which is neighbor. Before the node goes on to the child, or he goes, obviously it's a DFS traversal or it's a simple traversal which has to go to the child. If he goes to the child itself, he knows that he already has the answer for his subtree. But my child don't know anything about this portion. I just have to tell my child about this portion. That's it. So what I will do is, when I will go on to my child, I will give my child this information. What is this information? This information I have represented by even above and odd above, which means when the node will go and do a call to the neighbor, he will pass him how much is the even above and how much is the odd above, and you will see that this will help me to get the corresponding answer. That okay? Number of even above, number of odd above. As you can see that I'll simply pass him that, bro, for you neighbor, this is the count of even above you, which you don't know because he's a neighbor. He only knows about this, but he is the node, he's a parent, he knows about everything else. So he has the responsibility to tell him what will be the even extra for him, what will be the odd extra for him, which he cannot see because he can only see his subtree, but node can see everything. So how he will compute it? Very simple. Node knows every, again. Don't imagine that node is also one of these subtrees. Imagine that node knows everything. Node knows everything. If node knows everything, then node will simply go and tell one that, bro, listen, you have at the even distance one node, which is yourself. Again, I have just represented these nodes here for your simplicity, but this values are nothing much, just existing value itself. When node 0 has to tell something about even nodes, he will say, okay, for me number of nodes at the even distance are 3. Number of nodes at the even distance are 3, which is 0, 3 and 4. So if I have to tell him number of nodes at his odd distance, they will be 0, 3 and 4. So you realized for my neighbor, number of nodes at the odd distance will be nothing but number of nodes at the even distance of my parent, right? So I need to propagate odd above something, again, I'm not saying exactly 3, but something from the even count, or I should say from the even count, I should propagate that value to my child. But why not entirely 3? Because right now even count is 3 because 0 was considered, 3 was considered, and 4 was considered. What if I had one more node? I had one more node named, let's say, 8. For node 0, this node 8 is also at the even distance. So the even count would have been 4. When I'm propagating that specific value to my neighbor, I should make sure I'm not considering his children. I'm only considering everything apart from his children. So when I'll propagate to my neighbor, the even count for his odd count, when I say his, which means my neighbor's, my child's odd count, I will make sure what all count were there which were at his odd distance, I should remove it from this value of even. So from, to get the odd up value from the total even value, I will subtract the odd count of my children to get the odd up value. How many odd up are there? So if I quickly tell you what I did here is, from my node to my neighbor, I have to propagate this odd up, number of nodes at an odd distance above you. I simply told number of nodes at the even distance were 4. Number of nodes at the odd distance in its subtree of 1 were 1, which is 8 itself. So this 8 is actually at the even distance from node. So for this subtree of neighbor, I will subtract the number of nodes at the odd distance, so as, because again number of nodes at the odd distance are actually the number of nodes at the even distance of parent. So from even I will subtract the odd value of my neighbor so as to get the ultimate even count. That ultimate even count of a parent is nothing but the odd distance from my neighbor. There are multiple odd even, but I show with the help of diagram. If it's confusing, go and watch and listen that again. Thus, you will see that for the neighbor odd up value, I'm computing or getting the nodes, which is my parents' total even value, subtracting my subtree's odd value, thus getting the odd up, number of nodes at an odd distance above me. And thus I will pass it when I will do a DFS for my neighbor, I should say my child. And same way I will compute the same thing for even. How? For even up, get me the odd up value, or get me the number of nodes or number of total odd values which I have from my parent, which is the node. Subtract the even below me or in the subtree of me, that will be my total number of even upper values. Thus, if you have both of them, you will simply pass it to your specific child, so that now he knows everything, because currently he knows everything about his subtree, but now as you're passing some information to him, now he knows everything else entirely. And thus you can simply now solve this. So you see that how you are computing what my neighbor was missing, and then you are passing that information to your child, or I should say the neighbor. You're passing the information to your neighbor so that he can compute his corresponding total even and total odd. What he did after this will come up, firstly he will simply say that, okay, what was my subtree even value and which came from above, I'll simply add it. What was my subtree odd value with what came from above, I'll simply add it. With this fact, with this doing of 2 times DFS, first DFS I computed the actual subtree even and odd distance number of nodes, Then in the next subtree, I am using or leveraging that specific pre-computation done to find the total even, total odd, right? And this is for my tree 1. Same thing I have to repeat for my tree 2 as well. So as you can see, the same stuff will happen for tree 2, which is DFS1 for tree 2 and DFS2 for tree 2. And again, when this is done, this is the main portion why or what makes this problem hard. Next all is pretty same as what we did in the first problem. We made the graph, then we initialize those 4 arrays, even subtree 1, even subtree 1, odd subtree 1, totals even 1, odd 1. This is for the tree 1. I'll simply do a DFS1 in the tree 1, DFS2 on the tree 2, DFS1 for computing these two values and DFS2 to compute these two values. Same way, I will do the same thing for my tree 2 as well, DFS1 and DFS2. When this is done, I have to find the golden node in my tree 2. So to find the golden node, or I should say, actually the count itself is what I require, which is the maximum total odd count for tree 1. We have to find the nodes having at the even distance, which means ultimately in tree 2 that should be the odd distance, because one edge will automatically be counted. So if one edge is counted in tree 2, I have to find now the odd distance from that specific node, golden node. So I will just check who is having the maximum odd count, or I should say maximum total count in tree 2 will be my golden node count, or I should say the golden node is this and the corresponding count is maximum to total odd, and that is what I will simply add it. For me, golden node as a node doesn't matter. If they ask me the corresponding node, I can give it here, but that doesn't matter for me. Then I'll go on to all my nodes. I will compute for every node what is the even. I'll compute for every node that pre-computed golden node count, which is the max total odd, and that is my corresponding answer for every node. With this, the time will be nothing but O of n plus m, because you only did DFS traversal 4 times, 2 times on tree 1, 2 times on tree 2. That's it. Cool. And obviously the space used will be all the nodes which I have, which is O of n plus m again. Cool. I hope you guys got it. Before, if not, I highly recommend go and watch that portion, that crux, when I was telling okay, distance or even, because it's a bit tricky if you don't write it by yourself. Cool. Bye bye. Take care. Do follow us on Twitter. There's a lot of content which comes up there, and there's a lot of updates which comes up here. And for updates primarily and to interact with the folks, Telegram, Discord will be the best. Bye bye. Take care.